Today we are going to discuss on the matrix approach to simple linear regression. Actually, this matrix approach is required for multiple linear regression. But before going to that, uh, it's easy if we discuss and sort things out here because you are familiar to simple linear regression now. You know how to estimate the model parameters, you know the values of them, and so putting them into a matrix and trying to approach from that point itself, I think it would be very easy for you all to catch up things. This is not hard. You all are applied math students, so matrices are just something very easy for you all, maybe easier than me sometimes. So anyway, this is going to be something easy. You have a bit of computations, but easy computations and some matrix computations just to practice things, but everything is known to you all. So we are going to introduce how to go with the matrix approach to simple linear regression in today's lecture. Right. Basically, this is the normal error regression model. Now we have overdone this. So what does this imply? We have n number of observations. N is our sample size. So I is the indicator here, right? So I can take values from 1 to n. So this implies, so y1 is equal to beta naught plus beta 1 x1. I is substituted the value 1 here and error 1. So likewise, we can come up with n number of equations. So generally, this is the normal error regression model. It implies this. If we write the model for each and every observation, this is how you write. I think that is easy to understand. So why we expand this one is because we need to construct matrices and go ahead in matrix computations. Above n equations can be represented by matrix and vectors. Actually, vectors are again some matrices, either column matrices or row matrices, right? For example, n by 1. It's a matrix, at the same time it's a vector, right? 1 by n, similar thing. So it can be expressed as in a matrix notation like this. So usually matrices are denoted by capital letters. If it is vectors and if it is typesetted, you can bold the letter, or either you can put an underline. So you all know how to write a vector. So it's okay to call this thing a matrix because it's a column matrix. Anyway, so why it is n by 1? Because we have n number of observations here, response variables from y1 to yn. It's usually written as a column. I know it's the same idea if you write it as a row, but with all the formulas, derivations, we take it as a column matrix or column vector. X is a n by 2 matrix. So the first column should be 1, because when you put this in here, right, it should give x1 times beta 1, x2 times beta 2, likewise. So you call this the data matrix or the design matrix. So these ones are there just to get the model. When you multiply things, you will see that you would be getting y equals beta naught plus beta 1 x only when you have this one. So that is something mathematics. And here you have all the data as a column. So corresponding to this observation, you put the value of x, the first predictor variable here. Actually, we have one predictor variable, so this is, we just have 2 columns here. If we go to multiple linear regression, you will understand that you have several columns here for several x variables. This is just one x variable. And in that, these are the x levels that we are talking about. This is just one x variable, one y variable. This is simple linear regression. Okay, one predictor. Here, beta, this is what we are going to estimate. So this is again a beta vector. It's 2 by 1. It's also going to be column arrangement. First thing is beta naught, the intercept parameter. Second one is the slope, beta 1. Here, this is the error. So since we have to get this arrangement, so beta is a vector, it includes beta naught and beta 1. So this is basically the matrix representation of the regression model, right? It could either be simple or multiple. It really depends on the value here, right? If it's n times, let's say p plus 1, 1 is for this. And if we have p number of different x values, this dimension is going to change. And based on that, this is also going to change, right? So this is n by 1. So when you do the math here, the product will give you again n by 1, 2 cancels out, right? Here also n by 1, so this is correct. This is the arrangement. This one is equal to x times the beta vector and this error. So when you do the math, when you do the multiplication, this one is equal to, how do you do this? This times this times this, likewise. So beta naught plus x1 beta 1. That is the first argument. So you all know how to do matrix multiplication, right? This thing times this. 1 times beta naught is beta naught. X2 times beta 1 is beta 1 x2. Likewise, you are doing it for all the n number of observations manually. This is this one. So, you know, again, matrix addition, you can, when you have the order like this is n by 2, n by 1. This is again n by 1. So you can add it to another n by 1 matrix. This is just one element, right? This one plus this one. Basic matrix computations. So it gives you this one. If you have any questions, please ask, maybe in the chat room or however, you can unmute and speak at any time. I'm just going continuously. Right. Simple linear regression model with normal error structure assumes that this one, this one, this one. What do you need that? Error, expected error is 0. Variance is constant, right? So it can have some constant sigma square. This is the notation used to this, right? We discussed this in, I think, second or third lecture. Variance of error is, this is the notation that we are using, right? This is my notation actually. So it is constant. This is not sigma squared I. That means it is depending on the level of x. No, this is just sigma squared for any level. And errors are independent. So in matrix form, it can be represented by this. Expected value of this matrix is again a 0 matrix, right? Vector or matrix or whatever it is. So expectation of each and every error is going to be 0. So the condition that error terms have constant variance sigma squared and that all covariances between each error term is 0. When I is not equal to j means we take 2 different error terms at a time and the covariation should be 0. That means errors are independent. If they have some dependency, there should exist a covariance. But no, the variance is constant, no correlation or no covariation between 2 terms. And this is the variance covariance matrix. We know the covariances are 0. So this is an n by n matrix for all the error terms we are getting. So we have E epsilon 1 to epsilon n here, epsilon 1 to epsilon n here, right? That is the variance covariance matrix. So, uh, these are the constant variance between these errors. So epsilon 1 variance is sigma squared. Epsilon 2 variance is sigma squared. It is constant throughout the process. No covariance. So we can write this like sigma squared I. I is the identity matrix, which you have ones in the diagonal, right? So this is just to give you some idea about matrix derivatives, just like we know the derivative of sine x is equal to cos x. So likewise, even matrices have their derivatives. So this is just for your knowledge. Just go through this. So if A be a k by k matrix of constants, A be a, so this is A, be a k by 1. So this should be bold type actually. It's a vector of constants. So this is a matrix, a symmetric matrix, no, symmetric, but k by k matrix. And this is k by 1 vector of constants. All these are constants. And y be a k by 1 vector of variables. So let's say z is equal to A transpose y. A transpose means it's becoming 1 by k, right? Times y. This is k by 1. Otherwise, we cannot multiply. If we don't transpose this one, we cannot multiply, right? And when it is, when the derivative is taken subject to the vector y, you are ending up with the vector A. So that is the first thing that you have to learn in matrix derivatives. So this is actually used in proving process. I might not question about this in the exam, but what I want you to have some idea about is that these also have derivatives. If you are interested in how the estimation process go with the matrix representation, you are going to need these things. But at the exam, I won't be testing this. But anyway, these are used in the derivations. Because, you know, we get the maximum likelihood estimator to obtain the estimators of beta naught and beta 1, right? So how are we going to get the maximum likelihood estimate? We are going to take the derivative with respect to y, and then we are going to maximize the likelihood, right? So to maximize, we have to equate the derivatives of 0. So to do that process, knowing the matrix derivatives is important. I don't know whether these are covered in any of your other courses. Just to make this note complete, I gave you how these derivatives work, and we are going to make use of it if we prove the estimators of beta naught and beta 1. But the proofs are omitted for this course. This is an applied course. But if somebody is interested, you can make use of these things and try to prove the estimation formula of beta naught and beta 1 using matrix approach. So if we take this quantity y transpose y, these are vectors, and we take the derivative with respect to y, we are getting 2 times y. A transpose A, this is a matrix, this is a transpose vector y. When this is taken, when the derivative of this is taken, we are ending up with transpose of the matrix times A, right? It's like the transpose of this quantity, right? It is distributed. So here y transpose A y is going to be this one when we take the derivative. And if A is symmetric, you know, if some matrix is symmetric, the transpose of that matrix is equal to the matrix, because if it is symmetric, you can interchange the sides, right? You can interchange rows and columns, doesn't matter if it is symmetric. So if that is the case, this A transpose is going to be the same as A. So actually this is dabba by transpose ay over dabba by everything is taken the derivative with respect to y. So this is actually gone down, sorry about that. So this is going to be ay, and then the addition is 2 times ay if a is symmetric. So those things are going to be useful in either ordinary least class or maximum likelihood. So I was talking about maximum likelihood. There you have to get the derivative and maximize it, right? Here, ordinary least squares estimation, how do we do? We get the error, squared error term, squared sum of error term, and our intention is to minimize the error. So we equate this to 0, right? So if Q is the error quantity, you can substitute the model here, right? So in matrix notation, now you know how to write this, right? So this is this times this, say A times A, something like that. So when it comes to matrices, it should be A transpose times A. You all know it, right? You can't multiply 2 matrices in the same order. K times 1 times K times 1, you can't have that. But 1 times K times 1, you can do the thing. So if this is A squared in matrix notation, it should be A transpose times A. So this is how it's defined. So Y minus, these are matrices of, this is a vector, this is a vector, this is a matrix. When you can call these matrices, it's okay. So Y minus beta naught plus beta 1 xi is what? X beta. X beta is this one. Sorry. X beta is this one. Okay, that is understood. So they have taken the cross products here and expanded these factors and come up with this. So this small dash is for transport. Transpose is to denote transpose. There's another notation, capital T, superscript capital T is again used for transpose, right? You can use either of the notation, but make it clear. Don't confuse this one with inverse. Inverse is -1. That is 1. Actually, this is a dash. This is not 1. So I think it's better to use capital T to avoid confusions. Yeah. So to find the values of beta that minimizes Q, right? You have to minimize the error. You have to take the derivative with respect to beta, right? Because we are going to minimize the error with respect to the beta vector or the matrix, right? So to do this, I have not shown you the derivation here, but to do this, you have to make use of these things. That's why it's given in the note, but the derivation is not tested and we are not interested about the derivation here, but if somebody is interested, they can try this out. And this will end up like this. So if we have to minimize this, we have to equate this to 0. Actually, the 0 vector, right? Not just 0. These are all vectors, right? So when we equate it to 0, what will happen to this 2? It will cancel out, because if we divide it by 2, half times 0 vector is again going to be the 0 vector, right? So we are ending up x transpose y plus x transpose x beta. So we have to isolate beta. So beta is going to be equal to x transpose x inverse x transpose y, right? So that is that. So how do you estimate beta? Beta hat matrix is equal to x transpose x whole thing inverse times x transpose y. This one. Okay. So use matrix methods to obtain the estimated regression coefficients for AR freight break-in example. This is the data set. Yeah, so before going on to this, let's discuss this example. You can slowly do this with me so that you can practice, but at the same time you can watch this and do it later on, because there is an exercise for you all to practice. At the very end of this, you are asked to compute these things. I hope to give this to you as a homework, but just to give you some idea, let me do this with you. So our intention is to apply matrix notation to this. We know the formula now to estimate the beta vector x transpose x inverse x transpose y, right? So you have to know that formula, or else you have to derive and get it, right? The concept is minimizing the least squares. So just like that, you can even maximize the likelihood, right? This is easier. So let's start. So we have to have a y vector initially, then we have to have the x vector, right? So we know the formula to get this one, right? I know it by memorizing. I have done the derivation, but I know it by with memorizing. So it's better for you all to know. It's easy. X transpose x inverse x transpose y. So we have to compute the quantities x transpose x, x transpose y, and we have to get the inverse quantity of x transpose, inverse of x transpose x quantities, or likewise we have to do a couple of computations. But it's not that hard because the sample size is 10 and there are so many repeated stuff here. So these are very small values. So even by hand you can get this. I know in your calculators you cannot, I don't know, in my calculator I cannot enter 10 values. So you have to do it manually. If when the sample size keeps on increasing, you have to do it manually, but it's not really a big deal. We'll start. Any questions? Any unclear things before starting? The chat room says no. Okay. Right. So let's start with the y vector. At the exam, you don't have to write y vector separately, x vector separately, and then no, just you have to compute x transpose x quantity, get the inverse. Then you have to compute x transpose y quantity, multiply it and show. So but why I'm writing this x vector and y vector is just to show you. If you want, you can write it, but marks won't be allocated for getting the x vector and y vector because it's obvious, right? It's given in the data set. It's just the matter of copy pasting from the data set. So this is the y vector observations in order. 2, 13, 8, 15, 19, 11. So in today's lecture, actually more than statistics we have to do. Algebra. So this is, we have the sample size is 10. So we have a 10 by 1 vector, right? So what is our x? Actually, it's going to be a matrix because in order to get the x and beta multiplication, we have to have a couple of ones here, right? How many ones? There are 10 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here you have to have your data set. 1, 0, 2, 0, 3, 1, 0, 1, 2, 0. So this is basically a 10 by 2 matrix. Remember here, this one is corresponding to this one, right? This is corresponding to this one. True that there's no order here, but whichever the order that you are following here, it should be compatible with this. For example, if you put 9 here and 16 here, right? That is okay data are independent, you can go in any random order. But here also, then you should put 0 here and 1 here. Remember that. So why to make confusions interchanging things, right? No need. So just make it concise. That's all I wanted to say. Right. So by using these things, I'm going to compute this quantity x transpose x. I'm going to compute that quantity, and then I'm going to compute. So this is our goal, right? First, I want to compute this quantity. Then I'm going to get the inverse of that quantity, right? You can simply use your calculator to get this because this is a 2 by 2 matrix. It should be 2 by 2 because see, x transpose times x. So transpose of this times x is 2 by 2. So inverse is also again 2 by 2. So you can put that in the calculator and get it. And you have to compute x transpose y, this quantity, right? And finally, you have to compute your estimated beta vector, right? That is basically beta. You are getting the values of beta naught and beta 1 at the end when you do the computation. So how do you get it? X transpose x inverse x transpose y. So you have to compute these quantities in order to get this one. Finally, this is the final goal. Our intention in today's lecture is applying matrix approach to simple linear regression. So this is simple linear regression. We have just one x variable. This is simple linear. We don't have multiple x's here, right? So we practice how to compute these things and get this one. This one you should know. X transpose X inverse X transpose Y, right? How did we get this? By OLS method, ordinary least squares method. We minimized the squared sum of error, and by using those derivative approach, we end up getting this one. In the lecture note, this is not directly given. It's better if you can write it there. So what you should do is equal this to 0 vector, n by 1 vector, right? Then what will happen when you do the math? You have to isolate beta here. So beta is equal to, this is going this side, right? And then you don't divide by matrix, so you take the inverse, right? Just let me do that here. Otherwise, I hope you understand this, but why? I'll put T here instead of dash. So what we do here is we equate this to vector 0. It's a vector. So this is going to be X transpose Y plus X transpose X beta, because these two cancels out. Then we take this to the other side. So here we are left with this. Okay. And to the left hand side of each, we are taking the inverse, right? We usually don't put it here divided by X transpose. That is not the way it's written, right? We can't divide matrices. What we do is multiplying it by inverse. So when we isolate beta, we take the inverse of this to the left hand side. So it's going to be X transpose X inverse times this quantity. So this is how we get this, right? That is the derivation. So knowing this is enough for this course. Right, so let's compute these quantities. It's easy. So what is this quantity now? I'll just show you the steps. you know, when getting this quantity, you really don't have to show the steps. It's fine, right? It's simple. In case if somebody finds it difficult too, I'm doing it from scratch. Yeah. So this is 2 by 10. Zero, 2, 0, 3, 1, 0, 1, 2, 0. This is 10 by 2. So you have to get a 2 by 2 matrix. That of course you know. So once 1 times 1. So you have 10 times. 1 times 1 is 1, 1, 1. Likewise, you have to add it. You have to keep multiplying and adding it 10 times. Right. Then here, these ones times these ones. So it's just a matter of adding these things. 1 plus 2 plus 3 plus 1 plus 1 plus 2. So that is 10. Here, same thing. So whatever comes here should come here. No? It should be, right? This times this. Then this times this. It's like getting the square of each of these element and adding, right? So in the calculator, you can just type 1 square. You can type 1 plus 4 plus 9 plus 1 plus 1 plus 4, right? Square of these. Others are 0. It's going to be 20. And our next goal is to obtain the inverse of this, just because the formula has x transpose x inverse, right? Either you can manually get it or just enter this value to the calculator and get this. Just show how you compute this, how you compute these quantities. Marks are given for computing this one. So the method is not required. If you write, that's fine. So because this can, without writing, this can be thought about, right? Just you can think and get it. So for this one, you will be getting marks. And getting the correct inverse, you will be getting marks. So you have to mention this one, this one, this one, this one, and of course you have to get x transpose y matrix. I think that is hard to get by no, it's also not hard in simple linear thing. Actually, it's not really hard to. Just to show you the method, I'll do it in another page. But there also I'll be giving it for the end vector. Next quantity is x transpose y. I'll just show you the method. So transpose of x is this 1 0 2 0 3 1 0 2 0. This is 2 by 10. I always write this so that I can make sure I'm writing in the correct way whenever I do a matrix computation. I know you all know this, but you have to get used to do these computations without making any mistakes, because a small mistake in one place will lead to huge errors. So this should actually be 2 by 1 vector. So 1 times this means you have to add all these. So that will give you 142. So this times this, you have to make use of a calculator. So that will give you 182. So I'll be giving marks for this one. You have to compute these quantities separately, this one, and this one separately, and show. So your end goal would be estimating the beta vector, right? That is x transpose x inverse x transpose y. So we computed this quantity. We are going to substitute that here. 1 over 5, negative 1 over 10, negative 1 over 10, and 1 over 10. is a 2 by 2. We expect a 2 by 1 matrix vector here. This quantity is this. Right, so you do the math and you'll be getting this. You can use the calculator for this. What have we got here? If you check the upright example by using the normal equations, normal formulas, you got this value for beta naught hat. You got this value for beta 1 hat, right? So even by using matrix notation, generally you can obtain these two. So this is our end goal, estimating beta naught and beta 1. So here you can say beta naught hat is equal to 10.2, beta 1 hat is equal to 4. It's very easy. Is this understood? You'll be thinking why we have to do all this. We could have easily gotten this by the formula. Yes, but when it comes to the multiple linear regression, you have to adopt this method. There's no other way. It's very rigorous to go with the formula because actually the data matrix or the design matrix X changes. That is the name given to that. Either of these names. This one changes, like when we have, this is just for a single X. What if we have so many X's? Let's say this is human height. Let's say this is human weight. What if we have to include age also to this model? You have to have another 10 values here, right? But if we have to get the BMI or something like that, then again you have to add it here. Salary, you have to add it here. So whatever the variables that you need to include in your regression model should be added as data columns. So this one would be expanded. That is why we practice. First, we start this up with the by applying the matrix notation to simple linear regression to understand the concept. But the real use of this is going to be in multiple linear regression. Any questions? I'll give you time to write this. Just write it down. And if you have questions, you can ask now. Okay, I think you all have written this down, and the chat room says no questions. Right, okay. So this is how you simply do simple linear regression by using matrices, actually determining the model parameters. Right. Okay. Fitted values and residuals. So the regression model is this by matrix notation. And the fitted model is this, right? So when you fit the model expectation here, the estimated error is going to be 0, right? It's going to be a 0 vector, so we are not writing it there. This is the true model, this is the fitted model, y hat, and this is the estimated model, right? X beta hat, right? So X is here, beta hat is X transpose X inverse X transpose Y. So here, we give this quantity a name, right? X times X transpose X inverse X transpose. This is H, right? We just denote it for our future use. To easily determine, because this quantity is repeated so many times in some cases when we compute, let's say SSR, SSE. Yeah, so for our future derivations, we use this notation. H is called the hat matrix. It is symmetric and it has a special property. H times H is H. Because it is symmetric, you don't have to take the transpose of it. It is H itself as it's symmetric, so H times H is H. So you call this the idempotent property, idempotency, right? H is said to be idempotent, right? This property is called idempotency. Right. It's just a name given to this. So y hat is equal to H times y. You can simply write this. This is the true one. The vector of residuals is given by this. You know, the error is going to be the gap between the true observation and the fitted observation. Similarly, when it comes to this one, you have to get the vector of true values and get the vector of estimated values. How are you going to get this? You know the x values in your sample. You as long as you have estimated the model parameters, it's just a matter of adding beta naught to beta 1 plus corresponding x. You'll be getting y1 factor, right? Just like that, you can add beta naught and beta 1 x2, so that will give you y2 hat. Likewise, this is going to be again a vector of fitted values. So when you subtract these two vectors, you are getting the error vector, just the normal way that we did, right? So this one can be replaced by this. So if we use this property, we can simply say this is I minus H. I is the identity matrix, right? So I minus H times Y. Different representations. Okay, and variance covariance matrix of vector of residuals. So looking at this is also important because we have to check for model assumptions, right? We have to see whether the error variance is constant. We have to see whether the covariances between unequal error terms are zero, right? So using the above result, the variance covariance matrix of the vector of residual is given by this. In matrix notation, this is how you do. In general notation, this is just sigma squared, right? This is a matrix, no? Right? Covariance means actually this is not the covariance of error. This notation means variance of error, variance covariance matrix of error. Because the covariance of error should be zero, right? It shouldn't be sigma squared or anything, it should be zero. But in this matrix, in the diagonal terms, you have all the variance values. The other terms, you have covariance values. So this is the notation for the variance covariance matrix. It is coming in a matrix, all the diagonal elements are sigma squared and the rest should be zero. Just do this and see, you should get zero. You should get zero if there is no covariance, right? We assume theoretically it is zero, practically it really should get values which is very close to 0. It has to. And this is estimated by this. So, you know, sigma squared is estimated by the mean squared error, MSC. This is coming here. So this is again a matrix because I is the identity matrix, H is the hat matrix. So why did we use this notation here? It's easier to obtain these matrices, compute and see. So this variance covariance matrix is given by this one. This, if you know the MSC, if you know this, you can compute it. Estimated one. Variance covariance matrix of beta hat. Even for beta hats, you can do this, not only for the error terms, because, you know, yes, we get two values for beta naught and beta 1, right? One value each, but still that is based on the sample data, right? Also, it has some variance. That is why we constructed confidence intervals and all that for beta. It can be varied between some values, right? If we take beta naught, it has some variation. It's not constant. It's not the parameter because it's the estimated value based on the sample. Parameter is a constant, but we do not know the parameter value. What we do is making point estimators, making interval estimators, doing hypothesis testing and all that. You learned it in the inference course, mathematical statistics 2 course, right? So even for beta, you can compute the variance covariance matrix and it is given by this formula. X transpose X inverse times sigma squared. So this can be estimated by this. Just plug in the MSE value. So you will be getting the estimated variance covariance matrix for beta hat. I hope it is clear. ANOVA results. So once we got the model parameters, we have to anyway run the ANOVA table and check for model significance or maybe model adequacy, something like that. So suppose 1, this is the notation actually. It's a name of a matrix. B and n by 1 vector of 1s. So this is n by 1. You have rows which is equal to the sample size and all the elements are 1s. And let J be 1 times 1 transpose. And it is going to be an n by n matrix. This 1 times the transpose of it. This is the matrix. You have to use this notation in future formulas. So learn this. J is 1 times 1 transpose. 1 is a vector, right? So by using this notation, you can say summation of yi is given by 1 transpose y. Y is a vector now. Y is a n by 1 vector. 1 is again an n by 1 vector. So when you transpose it, it is going to be 1 by n vector. So 1 by n multiplied by n by 1, you are getting 1 by 1. That means you are getting a constant, right? 1 by 1 matrix or 1 by 1 vector means what? It is a constant. So to see if you can get this, you know the y values. Summation of all the y's is given by this. So you have all the y's here. Transpose. It's obvious, right? This is by matrix notation. If you want to write this, you are going to write it like this. You can try and see whether you are getting the results. You can use this formula and get a value. You can use this matrix approach and get a value and compare and see whether they are similar or not. They have to be similar. Next one. In SS computations, that is sums of scars computations, the source of variation computations, we need these quantities, right? You all know the formula, so we need these quantities. So in matrix approach, how are we going to get the summation of a squared terms? You have to simply get y transpose y. This is y times y now, but this is n by 1, this is again n by 1. You can't multiply it in that form. So you have to transpose one, the left corner, right? And make it a 1 by n, and this is n by 1. So you're getting a constant. You have to get the same value by doing this for what you got this part. Same thing, matrix notation. Here also, so this is the square of this, right? So square of this means what? This one transpose this one. That is how you square it. You want to square this one. The first thing transpose the same thing. And you will be getting this. Shall we prove this? So proof is not necessary for you all, just to show you. So we know summation I goes from n, yi is given by this one, right? If you want this, you can't put square here, right? This is matrices. This thing transpose times. This is just algebra. So how do you work with this when there's a transpose here? How do you distribute this transpose among these two matrices? You interchange the values and apply the transpose. So it is y transpose, y1 transpose transpose. So that is 1 transpose transpose. So that is 1 times this one transpose y. So 1 times 1 transpose. What is that? We gave a notation for that. 1 times 1 transpose is j. Right? So if you want to compute this quantity by using matrix, this is the formula. It should give you the same thing. Just like that, you can prove everything. Let's do it for homework. Yeah. And okay, write the following in matrix form. Shall we start doing this? This one, and this one. Yeah, that's the end. So shall we, I'll give you time. By using these, right, you can play around things by using these, right? Try to get the matrix form of these three. Actually, if you know this one and this one, the matrix form of these two, it's just a matter of getting the subtraction, right? SSDO minus SSE will give you SSR. So the challenge is to get this one and get this one using matrix notation. I'll give you time, and yeah, I'll give you some time to try on this. The equations are given, and try to come up with the formulas. If you have questions, please ask. Just quickly take a screenshot of this, then it's easy, right? And by using that, so actually you have the lecture note with you, right? So this is this one, this is this one. That's all what you want to. You want to know this slide, take a screenshot. You want to know this slide, take a screenshot. And then work on this. Just find this one first. I'll give you time. Excellent. One person has sent me the derived formula of the matrix representation of SSTO, and that is correct, exactly. So just because one person has done it, I'll do the thing on whiteboard for SSTO. The person who has already done SSTO can try doing SSE and SSR. So others, if you have not come up with the answers, can look at the board, and I'll give you time to do SSE as well, because once I do this for y'all, y'all should be able to do it for SSE, right? So this is how you compute, how you form SSTO in matrix notation. And thank you for the person who answered it. And thanks, brothers who tried it at least. So yeah, this is this. This is easy. So think about forming this with the notation that you already know. So you know the matrix notation for this, but you don't know the matrix notation for this. So what is y bar? You have to expand and then substitute. I goes from 1 to n yi squared minus, so n is here. We're going to have a square. So what is y bar? I goes from 1 to n yi divided by n. Do you agree? What is the, how do you compute the mean of something? Simple average. You take the summation of everything and divide it by number of observations. So here it is n. Now you know how to substitute. So this one, it is y transpose y. You have to take the square. You can't square it like this, right? You have to take a constant here, so it is y transpose y. Minus this n cancelled out with one of these n. So you have n times n here. So this would be 1 over n, right? So you are left with summation I goes from 1 to n yi squared. This one we just derived. It's this one, right? It's y transpose jy. You can either use this whole thing and get, if you can remember, you can simply add this, substitute this one, y transpose jy for this. So it's basically this is the answer what I expected from you. Easy, right? So the decision that you have to make is you have to reform this one like this, right? And then of course substituting the results that you know. Okay. Any questions with this? Is this clear?
Yes, madam.
Okay, thank you. And if this is clear, you should be able to come up with an answer for SSE. Quickly take a screenshot. And you don't need this actually to compute SSE. What you need is these things, right? By using these, just compute SSE. Now this is given. You know what error is, right? Error is the gap between the true observation and the fitted value. So you have to take the squared errors and sum. So yeah, I'm not telling anything. Do this and take the matrix notation for it. It's also a bit long. Yeah, just like this, it's long. The formation is long. Just to give you a clue, this thing has the final matrix representation has y in it, has beta hat in it, has x in it. Okay, so what I mean was here in SSTO, the final representation has y and j, right, with this n. So just like that, in SSE, you should end up having y, beta hat, and x. They should be there. Just a small hint. Try it. If you have come up with the answer, just drop a text in the chat. Okay, I'll give you more time. So try to think about this like this. Just assume you have EI squared here. What are you going to have? E transpose E. E is the error vector. That way is easier. Right? It's easier to go in that way. Try to go like that. Try to approach this without getting yi minus yi hat squared. Try to go it in that way. So this pattern. Just another hint. It's workable the other way, but it's easy to go like that. Try. Okay, I'll tell you how SSE is done. It's nothing different from the previous case. So they have given SSE is equal to summation I goes from 1 to n EI squared. So you can either do it by expanding this or expanding this in the sense substituting yi minus yi hat, or you can simply think about when there's summation and when there's something, right? This was this square. This was our approach, right? Something, squared, summation. So I told you to use that way. So from here onward, even you can use that notation, or you can even substitute and get, doesn't matter. So something, this one. Oh, it's not wrong to go it like this way. Doesn't matter. Same thing. It's the same thing. So this is again going to be something. Like when you write it like this, it's not visible that this is just one element, right? That's why I told you to go in this way. So what is this really? Same thing like this. You have y minus y hat transpose y minus y hat. Something transpose the same thing. Something transpose the same thing. Something transpose the same thing. So this is this. Right? You can either go in this way or you can go in this way. However it is, you know what is y hat. We discussed that. We show you if I think about because this is very easy, right? If y is equal to this one, y hat is this one in matrix notation, fitted model. Y hat is x beta hat. So you can either go in this way or this way, doesn't matter. So Anyway, even if you go in this way, you have to substitute y minus y hat for this, right? So whichever the way you identify, if you go in this way, you have one more step further to write. That's it, right? So I'll keep both the ways, but how do I say? This is one method, right? So even after here or here, the next step is error is what? Y minus y hat. So after this, you are going to have it like this. So from the first place itself, you can come like this, or by doing this, you can move here. So let me erase one part. So I'll erase this one, otherwise it's confusing. Same thing. This is the thought. Okay. So if it is error, it's the gap between the true value and the fitted value. So true matrix minus fitted matrix. So this is basically y hat, right? This gives you this. Now I think it's easy. Now you have to expand this. How do you expand this one? So transpose can be distributed. Y transpose y minus y transpose x beta hat right? Then this one minus x beta hat transpose times y, minus and minus is plus. You have to go in order. X beta hat transpose times x beta hat. You know, when matrix multiplication, you have to follow some order. So then what? Just have y transpose y here and y transpose x beta hat, right? How do you distribute the transpose? This is going to be beta hat transpose x transpose. I hope you all know it. Here also you're going to have beta hat transpose x transpose, that is this one, and this one, x beta hat. I don't have to do this, but to make it clearly visible for you all what we have done. Right. Then what is next? So then we are going to can you see here x transpose x? So whenever you see this, you have to recall something. What is beta hat in terms of x's and y's? Because you see this quantity in beta hat, right? We want to, you know, simplify this. Otherwise, we have to do a lot of math in order to find SSC. Still, this is workable from this level onwards, but we can further simplify this, right? So by looking at this quantity, what can you say? Beta hat is x transpose x, this quantity inverse something else. So when we substitute this thing inverse here, the terms get cancelled out, right? A inverse A is what? Okay, so from here onward, we have to think of a way of simplifying this. Although this is workable from this step itself, it's better to simplify. So when we look at this, we know that beta hat can be written in terms of this quantity, and there's an inverse coming, so it cancels out, right? So we can write this way. X transpose X, and instead of beta, we can write instead of beta, you can write X transpose X inverse X transpose Y, right? So this one actually cancels out. So we are left with beta hat transpose X transpose Y, right? So it is the same with this, right? Beta hat transpose X transpose Y. So let me write it in the next page. Beta hat transpose X transpose Y. Beta hat transpose X transpose beta transpose X. This is what we have. So this thing cancels out, and we are left with beta hat transpose. It's better not cutting that. So this is beta hat transpose X transpose Y. Right. It is this one. Right. So this is the same thing repeated here. So it cancels out, and you are left with Y transpose Y minus beta hat transpose X transpose Y. This is the answer. This is actually I, this one. Right, so this is the answer for SSE. Any questions here? Is this clear?
Yes, ma'am, it's good.
Okay, thank you. So we know SSTO and we know SSC, so it's just a matter of getting the difference for SSR is equal to SSTO minus SSE. So when you get the difference, write it. So this is SSTO and this is SSC. Remember the bracket because this is going to be plus. And this is cancelling out, this is going to be plus. So SSR is basically beta hat transpose X transpose Y minus 1 over N Y transpose J Y. Actually, you all have to know these because these are not given at the exam. So you have to know the matrix notation of SSR, SSTO and SSE. I won't tell you not to buy heart things, but you know, get things in practice. So when you practice these things by using different examples, you really get this into it, or else you can simply quickly derive and get if you know the initial formula. But I think it's time saving if you can remember. You don't have to remember SSR if you know SSTU and SSE. So try to come up with something which is suitable for you. But these are not given because at the exam, if this is given, it's just a matter of substituting things, right? So the derivation is taught for you all. If you can't remember, you can derive and get, right? There's enough time. Usually this would be given for multiple regression, not for simple regression, because in simple regression, we really can go with the basic formulas that we use. We have these things when we have multiple linear regression. So we are going to discuss on that next week, how to apply this matrix approach to multiple linear regression. I give you some idea about it. When designing this X matrix, you have to adopt columns for each and every X variable that you think of inserting in the model. So that's what you do. If you know these things, you can simply compute SSR, SSTU, and SSE, all these. But in multiple linear regression, we have to discuss some theoretical parts. It's not just the matter of applying on the desk. So we'll discuss about that in the next week's lecture. Thank you very much for participating. Before ending, there is one more activity you can. So we were here. This activity is just for you all to practice things. Now you know how to derive things when you are given a data set. We practice that by using a upright breakage example. This one, same thing that I work with you all. So you can try to compute this one by using this one, likewise. So this is all these formulas are given, right? What is this? You know how to estimate this one using MSE. So things like that. And finally get the ANOVA table. Now you know the matrix representation of these three. So it's just a matter of finding, substituting and finding the quantities and constructing the ANOVA table. And this is again a simple linear regression example. Please try this before next lecture. You can really do this. It's just the matter of substituting things to the matrix so that you can practice. This is not hard, you know. Matrices is not hard for you at all because I know you know this thing. But what you have to concentrate here is to correctly substitute values in the correct way and obtain the end result. Don't do careless mistakes because simple deviations from data in the beginning would give you massive differences. So it's going to be a waste. And always show the method so that you can score marks, right? The marks are given. If you are asked to compute beta hat, don't compute X transpose X inverse in a rough paper, and X in transpose Y again in a rough paper, and finally give the value here. What if you have done something wrong in computing this one? But what if you have gotten this one correct? So you are getting marks here, right? So if you didn't give these things in the paper, I don't have any place to give you marks. So please show this, and I will be giving marks for this because I don't know whether you computed it yourself or you grabbed it from someone else. So just show the method of computation. You don't have to write long matrices. That of course, if you can, by mind, if you can do the computation, you can do it. If you want, you can write the marks are given to final values. If I ask you to compute beta hat, I won't be checking how you computed this one, but you have to show that you have somehow computed this and keep it aside in the paper. Don't do it in rough sheet. Do everything on the paper, so that you all can easily score. So that is the thing I have to say. And do the assignment. I think around two people had submitted the assignment, and the deadline is on the 28th. So don't wait till the last minute. I know there are power cuts, so please don't wait till the last minute to submit your assignment. Tell your colleagues as well, because the deadline cannot be extended because it's given a 1 month's time. Whenever power is there, keep your assignment done and upload it as soon as possible. So you have time till 28th. So just an alert. Okay, so if you don't have questions, you all can leave the meeting. Thank you very much for participating in today's lecture. Stay safe.